Okay, so first with exponents, what we're trying to do with exponents is simplify expressions that look, something like this. And your instructions here are almost always simplify. I do want to remind you what it means to simplify. When we're working with exponent problems, number one, we want to eliminate parentheses. So when I see this problem, I don't like the parentheses there. Parentheses are like a restriction. I want to get rid of that restriction to make it simpler, easier to work with. Then number two, I want to combine what I call the like bases. So when I look at this problem, I see the base of x appears a couple times. I want to combine those all into a single x. That's going to make the problem easier for me. I also see that there's a base of 2, but that base can't combine with x. Those are not like bases, so that's going to be a whole separate thing. So when I look at a problem like that, I know my final answer is going to be like a 2 to some power and an x to some power. That's what I'm looking for when I combine the like bases. And the third step, which isn't in this problem, is we want to make sure we don't have any negative exponents. So no negative exponents. And typically that is the easiest order to work through these, but you can get to the right answer in other ways too. Right? So one kind of nice thing about exponents is you can take different routes and still end up at that same answer. So in this case, right, one of our sort of exponent rules is when I have an exponent on the outside, I have to apply it to both of the pieces or however many pieces are on the inside. So a lot of students forget to apply this 3 to the 2, right? But that should be 2 cubed. And then when I apply this 3 to the x squared, that is a multiplication rule, right? So I go through a whole list of these rules in one of the videos, but when you have an exponent applied to another exponent, you multiply those together. In the bottom here, I have x to the 4th times x cubed. So when I'm multiplying the like bases together, I add those exponents, which gives me x to the 7th. Now, I guess you could say this does have a little bit of a negative exponent here because I still want to combine these two bases together. I don't want both an x to the 6th and an x to the 7th. And the rule for that is anything on the bottom we can think of as a negative exponent. So if I want to combine these together, this plus 7, I can bring it up and think of it as subtraction, right? Or a negative 7 up top. The rule is kind of expressed in different ways, but I think that's a nice way to think about it. Whatever the positive or negative is on the bottom, when it comes up, it's going to switch signs. So this gives me 2 cubed x to the minus 1. And my third rule here is no negative exponents. So this x to the minus 1, I need to get rid of or rewrite. And the way to do that is to bring the negative exponent down to the bottom, which is going to make that a positive 1. Or you don't need that. You don't normally write that. So that's the simplified version of that original exponent problem. Let's try another one. Let's look at 3x squared y to the minus 4th to the minus 5 over x to the negative 13. It's a related problem for sure. So, when I look at that, I was just take a minute to sort of make sure I'm seeing it the right way. I see a base of 3, a base of x, a base of y, and another base of x. I see some negative exponents, and I see some parentheses. So I've got to kind of deal with all of those things. I'm going to start by eliminating the parentheses. Here I have 3 different factors inside the parentheses. So this x to the minus 5 needs to go to all 3 of those. Don't forget the 3. 3 to the minus 5. Just like before I multiply, I use the same rule. So 2 times negative 5 is negative 10. And then minus 5 times minus 4 is positive 20. Any questions so far? So hopefully what you see here is you see these 2 x's, which I need to combine. When I bring the negative 13 up, it should become positive 13. So I have 3 to the minus 5 x cubed y to the 20th. So this is good. I've got the like bases combined. And now I need to get rid of the negative exponents. That's this piece. These I don't want to change, so I leave them in place, but this 3 to the minus 5, I want to make that a positive exponent. You can multiply that out. 3 times 3 times 3 times 3 times 3 if you want to, but it's perfectly fine for me just to leave it in that form. Okay. Any questions? So we also want to look at polynomials here. Remember that polynomials are a certain structure. They're like a mathematical structure. So 3x to the 5th minus 2x plus 17. This is a polynomial. It has a sum or a difference of these different kind of chunks, if you will, that we call terms. So this one has 3 terms, separated by addition or subtraction. So we would call that a trinomial. It has a degree, so all polynomials have a degree. The degree is the largest number of variables in any of the terms. Right? So this term has 5 x's. That's bigger or more than any of these terms. So the degree of this polynomial is going to be 5. For each term, these parts are called the coefficients. That's like the numerical part of a term. And this part's called a constant term, since there's no variable in it. All right, so there's a little bit of just vocabulary, making sure we can talk about polynomials properly. Once we, oh, sorry, let me take a look and make sure I hit all the. So once we have polynomials, we want to make sure we can work with them. So do some basic operations. Adding and subtracting polynomials should be pretty straightforward. 2x cubed minus 5x plus 1 plus x cubed plus 4x. So this would be adding a trinomial and a binomial. And the whole key there is just make sure that you only add like terms. Like terms are the ones that have the same variable portion, right? So the 2x cubed and the x cubed, the minus 5x and the 4x, those can be combined, the other terms cannot. So the x cubed and the two x cubed combined to give me 3x cubed, the minus 5x and the plus 4x are minus x, and the plus 1 is just a plus 1. Just make sure you don't lose a term. That's probably almost the most common error here, is that people forget and lose one of the terms that they are working with. Subtraction is very similar, but because you're subtracting potentially a couple terms, you have to remember to distribute that subtraction. So that's really, again, the main error there. X to the fifth plus 2 minus 3x to the fifth plus x minus 7. Right. So if I'm doing the subtraction problem, I am going to take a minute and just make sure that I distribute that subtraction to all three of those. Negative 3x to the fifth minus x and plus 7. Right, I take that as its own extra step because I'm worried about making a mistake with the negatives. Now I can, again, combine those like terms together. And 2 plus 7 is 9. Okay, so again, I think for some of you that have the feel of that, those are very straightforward problems. If you are making some errors with those, we really want to make sure that we spend some time to fix that. We'll be working with polynomials. Of course, you've worked with polynomials in this section. We'll do it after the midterm and even after that. So there's a couple more sections where we'll be spending time with polynomials. You got to make sure that you've sort of mastered how to work with those. And then finally, we've got some multiplication problems. And multiplying uses a little bit of our rules of exponents, but it's a lot about just making sure you're combining the terms of the polynomials properly. So for instance, 2x squared times x cubed plus x minus 7, right? This is the distributive property. This, we have a single term on the outside, so that is going to get multiplied by all three of those terms on the inside. when you're working with polynomials, you really want to organize by term, right? So when I look at a polynomial, I'm always breaking it down into how many pieces or terms are there. So each of these, then I can figure out sort of independently. 2x squared times x cubed is going to be 2x to the 5th. 2x squared times x is 2x cubed. Right? And minus 7 times 2x is minus 14x squared. So there's our answer that we're looking for. So that's a monomial, or a single term, multiplied by a trinomial, or those 3 terms. A lot of times we are multiplying binomials together. Something like this. And I'm hoping that a lot of you are using the FOIL method, right, which is just a way of organizing how all those terms go together, right? So we multiply the first terms together. We multiply the outer terms together. The inner terms are these two. And then the last terms, right, the 2 and the minus 3. It gets a little messy, right, when you try and combine it all like that. But it doesn't matter what order you have those in, but you do need to get all 4 of them. So that's what the FOIL method is helping us remember, right? And typically when we do that FOIL method, these inner and outer terms, or these middle terms, can be combined together. Notice those are like terms. So I get 2x squared plus x minus 6 as my final product, right? What happens when I multiply those together. Foiling is very versatile. It works with any binomial. There are sometimes some shortcuts, but you'll always do fine if you use the FOIL method. One type of problem I would like to remind you of. Here's a binomial squared. I have a lot of students that make an error with this one. They try and distribute the squared to both of these pieces, and that's not something that you can do. We don't have that rule of exponent. The safest way to deal with this one is just to remember, when you square something, you're multiplying it by itself. And if students do that, then they typically FOIL and get that problem correct. So you just want to make sure that you see this problem, and that you don't see, I don't even like to write it down because it's wrong. Something like that, right? That's not correct. You have to FOIL it out. And that's I see that all the time, right? Every test I give that has a squared binomial, a couple students will always take this route, but we need to be taking this route. Now we can FOIL it. X squared times x squared is x to the 4th, minus 3x squared, minus another 3x squared, and a plus 9. So that's x to the 4th minus 6x squared plus 9. And if you've done enough of these, you can make a little shortcut here. There's a pattern. The book, I think, calls it like a special product. So x squared times x squared gives you the x to the 4th, and the minus 3 times the minus 3 gives you the 9. But you also have to remember that I'm going to get 2 of these middle terms, minus 3x squared and another minus 3x squared, and that's what gives me the minus 6x squared. So if you're feeling confident about these, you can certainly make a shortcut and get here directly. I don't know that the shortcut saves us that much work. I'd much prefer you get this one correct, right, first, and then we can worry about a shortcut or speeding it up if we need to. The other special product they talk about is when you have a product that looks exactly like this, where you have a one that's positive and one that's negative, and otherwise they're exactly the same. When you have that pattern, again, I'm just foiling here. 2x times 2x is 4x squared. 3 times 2x is 6x. Minus 3 times 2x is minus 6x. You'll notice, right, those are exactly opposites. So those two are going to cancel. And in fact, with this pattern, those two cancel every time. So I don't even actually have to ever multiply those out. I know they're going to go away. So I really just have to do the 2x and 2x, and then the plus 3 and the minus 3. So I just get that 4x squared minus 9. And again, the book calls that another special product. If you do enough of these, you'll just discard these middle terms right away, and you won't even think about them. But if you just go ahead and FOIL it normally, you'll get the same answer. So I don't think it's so critical that you use those special products. It's helpful, but you can get there with other methods. Okay. Any questions on any of those examples?